Hi and welcome to this third video in the mini-series of Kinetics A2 videos, and in this one we're going to look at the rate constant. In the previous two videos we looked at the rate equation and subsequently ways of deriving the rate equation from initial rate data, and we have been able to figure out equations such as the following, where rate equals K, which is the rate constant, multiplied by a concentration to a specific power. In this one we'll say it's the first order reaction. And K is the value which links the concentration to the rate. It's the proportionality constant, the rate constant. And it will have a numerical value which can be calculated by rearranging the equation to derive what K will be, and you could use some of the values in a question. If you're given this and you're asked to calculate a numerical value, you would plug in the values for the rate and also the corresponding concentrations to numerically derive K, but you will also be asked to evaluate the units for K as well. And K's units will change depending on the overall order of that reaction. So if we look at this example being a first order reaction, we know that the rate is going to be fairly standard and is going to be in moles per litre per second. And on the bottom we're going to have a concentration term, which in this situation is going to be first order and will have a singular unit of concentration. This therefore means that we will be able to cancel out this concentration term on the top with the corresponding concentration term on the bottom. This will leave us with a rate constant for a first order reaction of seconds to the minus 1. If we were to then compare this with a second order reaction, we'll use B this time to order 2, assuming then again that K is equal to rate this time divided by B squared, and again plugging in our units, moles per litre per second. That's going to be consistent on the top half of our sum here, and we will then have moles per litre squared on the bottom. Now what I'll do is I'll write it out slightly longhand, in that we will have moles per litre times by moles per litre on the bottom. This makes it easier this way, I think, to then be able to cancel out a singular version of the concentration, so that you then know your unit has been simplified to seconds to the minus 1 over moles per litre, and we therefore can't simplify that down anymore in terms of cancelling out. However, we can obviously bring the bottom half of that fraction to the top, and we do that by changing the sign of the powers of the units. So moles is essentially to the +1 when it's on the bottom, so when we bring it to the top we make it to the moles -1. And likewise, when we have a decimeter to the -3, when we bring it to the top, it becomes to the +3. And so we can see that we have a difference of units between both the first order reaction on the left-hand side and the second order reaction on the right-hand side. And it's a very common question asking you to evaluate what K is in terms of numerical value, so you don't have to plug values into your calculator, but also being asked to evaluate its units, because it's one of the few examples whereby the units will change depending on the situation of the question. In the situation where a reaction may potentially simply be zero order with respect to a reagent, then in this situation the rate will simply equal K, in which case the units of K will be simply the units of rate, in which case it will be moles per litre per second. a fairly rare example because that's a situation whereby the rate is not dependent upon any of the concentrations within the reaction. But again, using the same methodology, we're able to simplify that down. It's possible, as you would see with equilibrium constants, sometimes the units do get some large powers on there. It isn't unusual to see +9s and -9s, etc., -3s, etc. in rate constant units. But if you trust the methodology and cancel them down, you should be okay. The key to this one is to always substitute the units into a rearranged equation and then simplify it down. The rate constant is fixed at a specific temperature, and it will only change if we change that temperature. That's where we'll go next when we look at the Arrhenius constant, and we'll look at the relationship between temperature and subsequently the rate constant. But that will help us with rate constants in this one. And thank you very much, and I'll see you in video number 4.